Okay, for today's first class, I want to go back and revisit that problem on Friday that I had a problem with, and I was unable to find the mistake on Friday. But as I said at the last video, sometimes when you make a mistake and you're trying to troubleshoot in Excel, staring at it for longer is not going to help because it's more difficult to find your mistake sometimes. So I decided to take a little break, come back to it, look at it with fresh eyes, which I did over the weekend, and thankfully I was able to find my mistake, which is pretty significant, and fix the plot. And we see now that my red line, which is my modeled fit, actually goes through all the data points pretty well. So this problem again was developing a modeling approach that could characterize some experimental data. We decided to use the, the Virial equation of state with the Wilson activity coefficient model. So I'll pick up kind of where we left off with the general idea that we're going to use solver to solve for pressures, then use an equation to solve for y's, then use y's to iterate to find the new fugacity coefficients. And if you remember, when I left off on Friday, my red line was going way up like this, so I wasn't getting very good fit or agreement with the data. So I wanted to take you through kind of what my process was in troubleshooting the data. First of all, I noticed that when I had my gamma 1 and my gamma 2, if I compared from this down here is my experiment, is my not my experimental data, this is my modeled data stuff. This is my experimental data up here. I just visually did a quick check with my gamma 1 and my gamma 2 to see, well, did it match up with gamma 1 from the experiment and gamma 2 from the experiment? And that was a little tricky because I had different x points. So with my modeled approach, I have regular intervals for my x's, while in my experimental data, I only have a few x's. I don't have regularly spaced x's. So it was hard to compare gamma 1 and gamma 2 directly. So what I did was I made a quick plot. So the blue data points are my experimental gammas, and my orange line was my modeled fit for gamma. So that was the first thing I did to make a quick visual check. And I noticed that I did not have very good agreement at all. So now, as you see with this orange line, I have decent agreement. I still have some weirdness there that I'm not accounting for somehow. But the point is that most of the data points line up reasonably well. So I knew that my problem was with the gammas. And same thing with the gamma 2. I did a plot for gamma 2 as well. So I compared the modeled gamma 2s to the experimental gamma 2s. And I found that this line did not match up well at all. This line was way up here. So I didn't have very good agreement. So that was the first thing that hinted me off that, well, maybe my equation for gamma was wrong. And I ended up finding a mistake in gamma 2 relative to what I had written. But then I looked back in the textbook and I realized that the equation that I had for the Wilson model was completely wrong. So this was the equations that I had been using. This was the old one. This is the correct one. Notice that the mistake here is in this parentheses term. So I had neglected to realize that this term in the parentheses is the exact same for both gamma 1 and gamma 2. I had incorrectly told you that oftentimes gamma 1, gamma 2 have the same equation, but it's sometimes flipped. So whenever you have a lambda 2,1, it's supposed to be a lambda 2,1 in the other equation. That is not necessarily true. So go ahead and strike this one from your notes. Go back to wherever you had the Wilson equation and put this one in its place. The only difference, I think, is that the term in parentheses should again be the same in both. So once I had fixed that, I had another mistake, which was that my pressure that I was plotting in kilopascals was not the correct formula. So my pressure in kilopascals has to be my pressure, which was solved for using solver, divided by 1,000. So now that you've seen how it works, I wanted to kind of go back and redo a little bit just so that you can see that it does work and kind of follow along. So I'm going to pause the recording and back up a little bit. Okay, so that procedure one more time. This is the bubble point constraint equation that was derived using the same formula or the same algorithm that we use with Route's law and modified Route's law. That is, we constrain that y1 plus y2 must equal 1, and we add the equations together to obtain an expression that must be true. And in this expression, we have two unknowns. One of the unknowns is hidden. So P is the one unknown that is obvious. We also have Y that is included in this equation. That is a function that is in the mixture fugacity coefficient. So we have a functionality of Y kind of embedded within. And this is why we have to use this iterative problem solving approach. We can't just use solver outright. So what I've done is I have a column for the mixture fugacity coefficient for component 1 and component 2. And remember that the formula is from above. This is what the virial equation of state says that the phi must be. I also added a column for phi 1 guess and phi 2 guess. So this is going to get our process started. So because we don't know what Y is, we cannot calculate what phi 1 is. See, if I click on this formula, it's going to be referencing this cell, which we don't have a value for yet because it's unknown. So in order to make it known, we're going to make an initial guess for it, and we're going to go back and refine that guess. So a value of 1 will work reasonably well. Remember, 1 is the ideal behavior. So we don't assume that 1 is going to work, but we assume that it's going to be close. And then the phi 1 ratio is going to take that phi 1 guess and divide it by the saturation fugacity coefficient. So that, like I said, is going to get our process started. And then after the first round of solving, I'm going to copy these fugacity coefficients that we calculate and put them back in for phi 2 guess and start all over again. Now the constraint equation is, I kept that. I didn't want to type it all in again, so I'll just leave it here. I suggest that you pause the video and look at this equation if you want to look at it in more detail. P is going to be the thing that we are solving for. So I need an initial guess for P. Like I said in the last video, 600 would be pretty good because we know that the experimental data starts at about 550 and it goes till 1600. This column is going to be what I actually plot. So this column is going to be, just convert the units from pascals to kilopascals. So this divided by 1,000, and I realize that this column is going to be the 600. So I actually need to make this 600,000 because it is in pascals. All right, copy down and copy down. Now the Y formula is calculated just by rearranging the, not the modified Raoult's law, but the equilibrium constraint. So I just take P over to the other side because now I've calculated it, or I will have calculated it. So it's going to be based on the value of P. So everything else in this equation to be solved for, I'll do the same thing where I'll just leave the equation up for a moment and allow you to pause and look in more detail. And I'll copy the Y all the way down. All right, so now you notice that when I have a value for Y, my value for phi changes. But my phi 1 ratio is going to take the value from phi 1 guess. All right, so now what we have to do is use solver to solve for P. And I already have it queued up, I think. So I'm going to set the objective for M34, that's our first constraint cell, to the value of 0 by changing the cells in D34 to D84. So that is my column of P's in pascals. Subject to the constraints that all the other constraint equations must be 0 as well. Do not want to check this box to make unconstrained variables non-negative, and I click solve. Remember, this is going to take a little bit of time. If you're on your laptop, I definitely recommend choosing fewer points. So instead of 0, 0.02, 0.04, so on and so forth, go in increments of 0.1 the first time you do it so that it takes a little bit less time. All right, so this is our first iteration. As you can see, it's not great, right? And that's because we are using the phi 1s that we just guessed as ideal. So this is going to be, you could think of it kind of, well, no, that's not exactly true because we didn't use the ideal gas assumption in the rest of the problem. Okay, so now what we have to do is take our phi 1 that we calculated and copy those values into our new phi 2 guess. And we're going to do another round of solving. So I'm just going to highlight all these columns, right click and copy them, and I want to copy the values. Remember, it's very important to copy the values, not the formulas. All right, so now that you notice that I've copied my phi 1 guesses. Now my constraint equation is all off again. They're non-zero, so I need to solver it again in order to get it to be 0. And solver's nice because it keeps your same parameters and variables and stuff from the time before, so I don't have to go in and change anything. I can just hit solve. Obviously that changes if you're going back and forth and you're solving multiple things at a time. Let's do another round and we'll see how this line changes. Again, it should take a couple of seconds. Okay, and you notice that we're getting closer and closer, but we're still not exactly there. So this is a good visual check of a way to see how close you can get. Another way that you can check is you compare your calculated phis to the phis that you guess. And if they're reasonably close, you can say that the solution procedure has converged. Usually this method takes 2 or 3 times. So I'm going to go ahead and try it one more time by highlighting the column of phis, copying and pasting the values, and I'll pause and I'll just run the solver one more time. All right, that didn't take too long. That was just after 3 rounds. And now this is what I'm talking about. You go through and you compare. Phi 1 guess is 0.958. Phi 1 is 0.9579. So this is getting pretty close. I would say after 3 rounds, it's probably okay. You could go through and do another round or 2 if you really wanted to. I don't think you're going to get much better than this. So at this point, I would call this problem solved. Very happy that I was able to find the mistake, and I definitely recommend going through in your notes and striking out the Wilson equation from before so that you never get confused again, or just burn it into your memory like I have now, that the term in the parentheses for the Wilson equation is the same. All right, that's the end of this video, the end of this problem.